Hello, let's see some numerical based on electromagnetic induction. In this numerical one, an iron ring of 30 centimeter mean diameter having cross-sectional area of 100 centimeter square is wound with 500 turns of wire. If if the current through this coil is 2 ampere, calculate the energy stored in it. Take the permeability of iron as 1000. So here the length is given as diameter is given as 30 centimeters. So how will calculate the circumference? Circumference is nothing but the total length. So total length is equal to pi into d. It is pi into 30 centimeters. So I can treat it as 0.3 pi, 0.3 pi. So area is 100 centimeter square, means 100 into 10 raised to minus 4 meter. Relative permeability is mu r is equal to given as 1000, number of turns as 500, and current is 2 ampere. So let us calculate the first reluctance, because inductance is equal to n square upon s. So it is necessary to calculate the reluctance. Reluctance s is equal to L upon mu 0 mu r into a. So 0.3 pi divided by 4 × 10 raised to minus 7 into 1000, that is a relative permeability, and a is the 100 into 10 raised to minus 4. So substituting all this value, we will get 75,000 ampere turn Weber as the reluctance. So inductance is equal to always what? N square upon s. So n is equal to 500 square upon 75,000. So it gives me 3.333 Henry. So 3.333 Henry uh, is the inductance of the magnetic coil. So how will calculate the energy stored in the magnetic circuit? Energy stored in the magnetic circuit is equal to 1 half Li square. So that is 1 half into 3.333 into 2 raised to 2 square is it gives me 6.66 joule will be energy stored in the ring. Now let us consider the two coils. One coil, that is X is equal to 12,000 turns and Y is of 15,000 turns, lie in parallel planes such that 60% of flux produced by the coil X is linked with the coil Y. That is, if whatever the flux produced in the coil 1, out of that 60% that flux is linked with the coil Y. A current of 5 ampere in the coil X produces a flux of 0.05 milliweber. If the current is carrying the current of 5 ampere, then it produces the flux of 0.05 milliweber, while the same current, if I supply the same current to the coil Y, then it produces the flux of 0.075 milliweber. So we have to calculate the self inductance, mutual inductance, and coefficient of coupling. So let us do the calculation for coil X first. Coil X, number of turns are 12,000, current carried is 5 ampere, and flux phi x is equal to 0.05 into 10 raised to minus 3 Weber, that is 0.05 milliweber. So reluctance, I will calculate reluctance. Reluctance is equal to mmf upon flux. mmf is given by ni upon phi x. So ni is 12,000 into 5, that is nx into ix. 12,000 into 5 divided by flux, that is 0.05 into 10 raised to minus 3. It gives me 1.2 into 10 raised to 9 ampere turn per Weber is the reluctance of coil X. Then how will you calculate inductance? Inductance is equal to n square upon S, that is Lx is equal to nx square upon Sx. So it is given by 12,000 square divided by 1.2 into 10 raised to 9. So it gives me 0.12 Henry. So 0.12 Henry is the self inductance of coil X. Similarly, I can calculate for the coil Y. For the coil Y, number of turns are 15,000, current is same as 5 ampere, and the flux is 0.075 milliweber, that is 0.075 into 10 raised to minus 3 Weber. So how will calculate the reluctance? Reluctance is equal to mmf upon flux. So ny of iy divided by phi y. If I substitute ny, iy and phi y, I will get 1 into 10 raised to 9 ampere turn Weber as the reluctance of coil Y. Then reluctance and then inductance of coil Y is equal to n square upon sy. So 15,000 divided by 1 into 10 raised to 9, that is number of turns square divided by reluctance. So 1 into 10 raised to 9, it gives me 0.225 Henry. So how to calculate the mutual inductance? To calculate the mutual inductance, we know that K1 is given as 60%. That is, whatever the X flux is produced, the flux link with the coil Y is the 60% of coil X, that is phi X into Kx, is the flux link with the coil Y. So Ny into phi Y, actually here Ny into phi Y upon Ix, but phi Y is equal to Kx, that is the mutual that is the flux link with the linkage of coil 1 with the coil 2. So Kx into phi X. So 15,000 into 0.6 into 0.05 into 10 raised to minus 3 divided by 5, it gives me 0.09 ampere. Here Ny phi Y upon Ix, but phi Y is equal to Kx into phi X. So how to calculate the coefficient of coupling? Coefficient of coupling is equal to m divided by under root Lx into Ly, that is 0.09 divided by under root 0.12 into 0.225, which gives me the coefficient of coupling as 0.548. So this is the coefficient of coupling between the two coils. In the third example, let us study the iron ring. Okay, so we'll study this example in the next session. Thank you. So in this example, an iron ring of 10 centimeter in diameter and 5 centimeter square in cross-sectional area is wound with 500 tons of wire. For a flux density of 1.2 Tesla and relative permeability of 800, calculate exciting current, inductance and energy stored. Here the length is not directly given. The diameter is given as a 10 centimeter. So length of the magnetic path is equal to L is equal to pi into 10, that is 0.1 pi. So it is given by 0.1 pi, and the area is given as, so here 100, here the 10 is missing, actually 10 pi centimeter, that is 0.1 pi meter. So area is equal to 5 centimeter square, that is 5 into 10 raised to minus 4. Relative permeability is 800. So we'll calculate the reluctance. Reluctance is equal to L divided by mu 0 mu r a. So 0.1 pi divided by 4 pi into 10 raised to minus 7 into 800, and area is 5 into 10 raised to minus 4. After substituting this, we will get 6,24,998 ampere turn per Weber. The flux density B is equal to 1.2 Tesla. So I will calculate the flux from the flux density. Flux is equal to B into A, that is flux density into cross-sectional area. That is B is equal to phi by A, so that phi is equal to B by A. 1.2 into 5 into 10 raised to minus 4, so it gives me 6 into 10 raised to minus 4 Weber is the flux. So mmf is equal to flux into reluctance. So flux into reluctance is 6 into 10 raised to minus 4 into 6,24,998. It gives me 375 ampere turn. Okay, but mmf is equal to N into I. So we know that mmf is equal to N into I. So I is equal to mmf upon N. That is 375 divided by 500. It gives me 0.75 ampere. 0.75 ampere is the current. Then we'll calculate the inductance using the formula N square upon S. N square is equal to 500 square upon S is equal to 624,998. It gives me 0.4 Henry. So to calculate the energy stored is equal to 1 half Li square. Is 1 half into 0.4 into 0.75 square. It gives me 0.1125 joules is the energy stored in the ring. So let us understand the next example. If a coil of 200 tons is linked with a flux of 0.02 Weber when carrying a current of 20 ampere, calculate the inductance of the coil. If this coil is if the current is uniformly reversed in 0.2 second, calculate the self-induced EMF in the coil. So we had given the N is equal to 200, I is equal to 20, and the flux is equal to 0.02 Weber. So how to calculate the reluctance? Ni upon phi. You will give you the reluctance. Reluctance is equal to mmf upon flux. 20 into 200 upon 0.02. It gives me 0.2 into 10 raised to 6 ampere turn per Weber is the reluctance. And inductance is equal to N square upon S. That is 200 tons. That is 200 square divided by 0.2 into 10 raised to 6. So it gives me 0.2 Henry. So here what is given? The current is uniformly reversed in the 0.2 second. That is, initially the current is 20 ampere and final current is reversed, means it becomes a minus 20 ampere. Okay, so change, final current is a minus 20 and initial current is a 20. So what is the change in current? Minus 20 minus initial current is 20. So minus 20 is become minus 40, and it is in 0.2 seconds, so divided by 0.2. So di by dt is equal to minus 40 upon 0.2, that is minus 200 ampere per second. So induced EMF is equal to minus L di by dt. L is calculated as 0.2 Henry, so minus 0.2 into minus 200, so induced EMF is equal to 40 volt. Thank you.